In the name of God, I would like to welcome you to this set of lectures that I'm about to begin, which is about kinetic theory of gases. This is going to be an introduction, and I hope you would enjoy what I'm going to present and find it useful. So we begin with in the name of God. And these lectures is going to be about kinetic theory of gases. I think this is a classic example of the interplay between theory and experiment in physics. So what I mean is this subject on its own is an excellent example of the interplay between theory and experiment. So I'm going to write that. Classic and sweet. It is for me sweet. I hope you're going to find it as such also. So a classic and sweet example of the interplay between theory and experiment in physics. So what I'm trying to say is that in general in physics we deal with kind of two things, broadly speaking. One part is theoretical aspect, and the other part is the experimental aspect. We're going to talk about this within the concept or within the subject of kinetic theory of gases. These two go hand in hand together to make actually what we know as the subject of physics. So for this I'm also going to draw, I hope I can make it easy here. So we have on one side experiments or observations, and on the other hand we have the theory or theoretical directions, right? And there may be some other things also to add, but it is difficult sometimes to make walls between different things, but we'll just take this as some sort of a starting point. So between these two I'm also going to add something which I'm going to call, or is called, model building. So let me erase that. Model building. And the whole thing physicists in a way sort of can be presented like what physicists do is actually to move around these three things back and forth, sometimes in a non-linear way, or maybe non really in complex manners in some ways. So you can have these ideas and effort coming from experiments into the theory aspect, from the theory into the model building aspect, and back to the experiment. Okay, and one can also consider the reverse. So the interplay, let's say this time around, is starting from the theoretical path aspects of things, and then fed into the experimental aspect. And model buildings, one gets some kind of sort of feedback, say, from experiments for kind of sharpening or reshaping or throwing away some of the models that have been built. So model building also kind of fits back to theory. So in physics, a lot of this happen, and I will try to explain like this. Let me see, maybe we don't need a pointer, right? We can consider this blob thing moving to be a pointer. So I'm going to describe these three things also within the this subject that is called kinetic theory of gases. So actually within this subject there are experimental or observational aspects to it, and there are theoretical aspects to this subject, and one can also say that there is a model building path of the theory. Okay, so I'm going to start with one, which is the experimental aspect. Okay, for the experimental aspect, let's go to the next page. So I'm going to write here in black experiments. Or observations. And these observations are related to gases, since, well, as the subject says, we talking about kinetic theory of gases. Okay? Over the time, there are lots of them. Maybe we consider basically 3 or 4 here. So the first one is concerning the properties of gas. Okay, one of them is pressure. I'm going to write P here, mentioning it to be the pressure. So pressure is directly or inversely proportional to the volume of a gas at a given constant temperature. At constant temperature. Okay. The second one, second observation. So this is a result obtained by making some sort of experiment on gas, and this has been observed that if everything being equal, the volume of a gas is increased, then its pressure decreases, provided that the change in the volume happened at a constant temperature. The second observation is related to the volume and the temperature, that the volume is directly proportional to temperature. If you increase the temperature, then the volume also increases proportionately, provided that the change in temperature or change in volume is done at constant pressure. So here it's constant P. And a combination of these two observations can be put into this form, that we have pressure times volume of a gas is directly proportional to temperature. Okay, so this is an example, something which is done from experiments, something which has been observed, and the target is would like to have an understanding of the properties and behavior or dynamics of gas when we change some of its other properties. Okay, so like here we're talking about temperature and pressure. Okay, this is something which is observed, and we would like to have a theory which can explain that. Okay, so physicists like to do things like this, seeing and observing something, then they want to have a theory to explain it, they want to have a model to explain it, and also probably from that model to be able to make some other predictions as well, which, for example, the experiment, from the experimental side, those predictions can be checked. Okay. So another observation related to the behavior of gas, which I would like to mention here, is the third one, and I think that would be it. The behavior of perfume, for example, when sprayed. So fragrance of perfume sprayed. So if you have perfume sprayed at one end of a room, right, it takes some time, okay, before it reaches some other point, some other part of the room, right? So one would like to understand this because of this idea that we can find, we can show, or one can consider, one can imagine that the molecules making up a gas, for example, the perfume coming out as molecules, we consider those as gas. Usually they have very high speed. So if the speed are like in hundreds, for example, of hand, if I say something like an order of magnitude, hundreds of kilometers, for example, can I say per second? It may be an exaggeration, but it's okay. Then one would expect that when you spray a perfume, it shouldn't take time. I mean, one would expect that immediately we should be able to kind of find it on the other parts of the room. But this is not happening. So why? Why is it this way? Okay, this is another observation which can actually be explained based on the kinetic theory of gas, as we're going to see. So these are 3 points regarding experiment. We go next to the theory, the theoretical part. If I make this here to be theory. So the theory here, which we're going to use to try to formulate, let's say, another theory which we can use to build a model, and hopefully that model should be able to explain these three, for example, observations which I've just mentioned. Okay, so the base of this theory, I'm going to list them here. One is so classical mechanics, Newtonian, for example. So we can consider this as the theoretical base, Newtonian, or in general classical mechanics, whatever, Newtonian or some other forms of classical mechanics. Okay, one can imagine that maybe it's not straightforward to get these three kind of listed observations straight away from Newtonian mechanics, right? So, but we're going to see that. We're going to model the molecules of gas to be like small spheres, maybe with zero radius, so they're actually point-like particles moving around and bouncing off each other and the wall of the container. Well, we're going to talk about this when we reach the modeling part of these discussions, right? Secondly, because of the nature of the problem, that the problem at hand is we are talking about gases. So and usually for gases it's a huge number like of molecules, right, making up a gas. So usually the system we want to consider system has huge number. I'm going to clean that. Has a huge number of molecules, or sometimes we call them or atoms, or we call maybe particles, whatever, small little objects, right? And because of this, actually the system would in some way going to or we're going to have to consider combinatorials for addressing the system, right? So there's going to be therefore there's going to be combinatorics involved, as we're going to see, and also things about statistics or probability. The thing is, since the number of molecules is really huge, one can imagine that it's really going to be difficult to consider each one and every of the molecules making up the gas and then try to apply Newtonian mechanics that way to each of them, right? It's going to be difficult. Maybe in the examples part of this set of lectures, I'm going to show an example to illustrate what I'm saying, and then hopefully we can appreciate more. But for now, you just take my words, and I think one can imagine like it's a huge number, right? Avogadro's number of particles. So let's say 10 to the 23 particles, and you don't want to watch each and every one of those particles and then try to apply Newtonian mechanics in order to determine the dynamics of the system. So instead of doing that, usually one consider a probabilistic approach, or a kind of a big picture approach of the system. So this is where probability comes in. Because if you want to study or address the big picture or the average properties of a system, then probability theory is going to be something which is helpful. So from the theory path, there is going to be a probability aspect. And what I'm going to do next actually is to talk a little bit about probability theory and averages. Okay, given probabilities, how do we compute averages? Because we're going to apply that for the model we're going to make for a system of a gas. And then from there, we also going to make a theoretical definition of temperature using statistics, right? And from that, something called Boltzmann distribution is going to pop up. Okay, I'm also going to talk a little bit, a sort of revision to provide a self-contained course. So there's going to be these parts which I hope you maybe must have seen in some other lectures, in some other classes, but we're going to kind of review the basics and then make use of it. Okay, so using the statistical definition of temperature is one topic which we're going to look at more. The second one is the concept of probability and applying Newtonian mechanics, for example, within the context of the kinetic energy of molecules, making a gas. From there, we're going to cook up or we're going to drive some nice probability distributions. So once you have probability distribution regarding a system, then it's easy, or one can work to compute averages and other statistical properties. Okay, so this is it about the theoretical aspect. I'm going to move to the next page. So to say a bit about the model we're going to make. So this is the modeling aspect, and for this we're going to use the theoretical tools at hand. So use theory tools. Going to raise that. And the theory tools are just what I've mentioned before in the previous page. So probabilities and how we say plus Newtonian mechanics, right? So we're going to use this to make a very simple model of gas. Okay. A very simplified very simple model of gas. And that very simple model of gas is going to be called ideal. So the theoretical gas to be considered is the ideal gas. And the hope is we should be able to make predictions from our model. Hope, or the aim, is to make predictions. So using this model, we should be able to make predictions which should next be checked with observations, right? And as an introduction, what I'm going to say here is that using this ideal gas and the theoretical tools, we're going to compute something which is very nice, which is very important. We're going to provide a mathematical expression for flux of gas, right? So from now on, mostly, I think whenever the word gas comes, when we're talking about the model or the theory, yeah, you should have in mind that we're talking about ideal gas, right? So we're going to have some mathematical expression for flux of gas, and then from there we can compute things like, for example, we can compute the pressure of the ideal gas, and actually that would give us something which is called the ideal gas equation. Okay, similar to the experimental observation that PV is directly proportional to T. So this is something which we're going to predict, or which we're going to derive from this model of ideal gas. Okay, other things which can be computed are two. So there is molecular effusion. 3 is going to be viscosity. 4 is going to be thermal conductivity. 4 we're going to, okay, this is going to be 5 instead of 4, so this is 5. 5 is diffusion equations. So you can see these are things I'm mentioning kind of a foresight of what we're going to see. So the actual thing we wanted was, we wanted to kind of derive or make a theory, make a model which can explain the theoretical observations, right? So there's this theoretical, to explain the experimental observation that P is directly proportional to 1 over V when temperature is constant, or V is directly proportional to T when pressure is constant. In a way, when you combine these two, so the observation was PV is directly proportional to T. So we're going to find this, it is possible to derive this an equation. So the equation is called ideal gas equation. We're going to see what the constant proportionality constant is going to be, right, from this model. And also it's going to show us, the model is going to give us more. So it's going to talk about how you can make predictions about molecular effusion, things about viscosity related to gas. We're talking about gases here, or thermal conductivity in relation to gas. or how things diffuse. Okay, so diffusion, like in terms of number of gas molecules, okay, evolving with time, and with respect to position, how does number of gas change when you release them? So for example, for the case of perfume being released at one corner of the room, it takes time to reach the other corner of the room. We're going to see that from solutions of diffusion equation, or how some other things, for example, move, say temperature, also things like that. So these are extra things which we're going to derive from this model, and we're going to see that they all agree with experimental observations. Okay, so this is something which is very nice. And yeah, I think that's it. The big picture sort of introduction of kinetic theory of gas, and I'm going to stop here for now, and I hope you enjoy it and get it useful, and see you in the next meeting. Okay, goodbye.